All right, guys. Welcome back after break. I hope you guys had a good break. We went up to, for my break, we went up to Chicago for the St. Patty's Day parade. We didn't actually go to the parade because it turns out there's a lot of people at the parade. It's like 20 people deep, and we decided not to do that. We did see the river being dyed, which was kind of cool, but if you've ever been to, if you've ever seen it on TV, it looks like they're dyeing this giant river. It turns out they dye like 3 blocks. Like it's just one little boat that zips back and forth and dumps dye into the river. But it was a good time. It was nice to be up in Chicago for a weekend. So we were talking about, when we were last here, we were talking about graphical models. And I was debating a little bit on whether to jump forward to neural nets this week or to do a little bit more on graphical models. I settled on one more day on graphical models just because I think there's something that's important that we're going to see again and again called variational inference, which needs to be introduced somewhere, and I think a graphical model is a good place to introduce that. So when we talk about graphical models, what we're talking about is probabilistic models. They're called graphical models because we generally draw them as a bunch of nodes, and we draw connections to indicate some sort of dependency. So the one that we looked at the most so far was an HMM. So an HMM is a sequence model, meaning that we basically expand the model out for however many states we have in the input. Not all graphical models have to sort of vary in size. This is something that the HMMs do, but not all graphical models do that. Some of them are just sort of fixed sized. But in this case, this is sort of the HMM that we were talking about, where these Y's were observations over time, and the X's were some hidden state. That's a real simple graphical model, very straightforward. We show the dependencies there. We can talk about the fact that we have really 2 dependencies here. We have the probability of some Y observation given X, and then the links here are the probability of the next state given the current state. So it's sort of a chain model. Now we can draw graphical models any way we want. All we're showing with a graphical model is sort of the interdependencies of the different random variables. So I can draw it nice, like a nice chain like this. I can also draw a graphical model that looks something like this. I'm going to switch to purple. Fortunately, my purple marker is dying. My orange marker was eaten by my dog, and now all we have left is the brown marker, so it might be time for new markers. So this could be a graphical model. So what does that mean when we draw a graphical model like this? This basically says that I have 3 variables. We'll just call them x1, x2, x3, and the x1, x2, x3 all have some state that they can take on. We generally have been talking about discrete random variables. So let's say these are all binary values, and they have some dependencies. So the way I drew it here is I didn't put any arrows on. So maybe this value is the probability of x1 given x2 and x3. So you see how x1 is generally the variable here is generally the node, and then the things that it links to are generally what's in the set of givens. So that's another graphical model. We can draw these all sorts of different ways. Now there's classes of graphical models. Some of them have the an arrow here, and that means the dependency only goes in one direction. Sometimes there isn't an arrow, so in this case, that means the dependency is actually going in both directions. So in this case, the probability of x2 depends on both x1 and x3 over here. So notice that x1 depends on x2 and x2 depends on x1.
So in HMM, what does x1 symbolize? Like how is x1 related to our data?
So x1 is a, do you mean what does this, like the various symbols of x1 represent? Like
What are the possible values for x1? Is it just true or false?
So there's a lot of flexibility in graphical models in general. The ones we've talked about, we have generally talked about two different kinds. They've both been discrete, meaning that there's set number of states. They're not continuous values. One of them was, the one that we considered for sort of recovery of language was basically the states came out to be like the letters of the alphabet, and then maybe a space in order to recover language. So in that case, the X's were those states. The Y's were actually had the same set of states, because you're sort of, when we're doing recovery of language, we were talking about getting a garbled signal. All the Y's were this garbled signal, and then we were trying to recover the most likely set of X's based on some process. So the X's could be that, or they could just be a set of states that don't have any real meaning. So when we talked about speech recognition, we talked about the Y's had meaning in that they were some input value that we observed. So we did some clustering and got some clusters and stuff like that. And then each Y was a cluster number. And then the X's didn't actually have any intrinsic meaning. They were just a mechanism that ran sort of in the background to say that, we go from X to X with this sort of probability pattern, and any given X state generates this sort of Y. And so there they didn't really have meaning. They were just some discrete number of states.
So then what was the point of the one where it didn't have meaning? What were we trying to do?
You still can use it to recover what the probability of a certain pattern of Y's is. So you get some observations, right? And the way we used it with speech recognition is we took a bunch of observations of a word being said. And then we trained an HMM, which we learned the parameters, which learned the hidden states kind of transitions, how things are emitted. And then we came along with a new observation. And we said, was this likely generated by this HMM model? So maybe it was, maybe it wasn't. So what we did is we just found the probability of that new observation given the old observations that we've seen before. So if it's highly unlikely, then we could probably say that wasn't that word. If it was highly likely, then we could say, yeah, it was that word.
So when we write probability of xi plus 1 given xi,
Yep.
Realistically, it's kind of an understatement because we're doing probability that xi plus 1 equals this, given xi is this, and xi plus 1 is that, given xi is this, and xi plus 1 is this other thing, given xi is this. It's like the whole trellis that we're talking about, as opposed to just this single.
Well, remember, xi is only going to take a single value in the end. You're going to only have, you have a single set of observations, you have a single set of x's. Now you could find the probability of any set of x's, any set of y's. If you switch them around, you run them through the probability equations, you just do the big multiplication that comes out. You choose some, we get x, we say that x was state 1, 3, 1. That's going to have some probability associated with it. So we can, any given selected, sort of set of x's, set of x values is going to have a probability associated with it. And we can do a couple things. We can either we can ask what is the probability of this y, in which case, we have some observation y, we infer the most likely x's that match it, and then we can say the probability of that y is something. Or if we had both the x's and y's, we could say what's the probability of this set of combinations. If we have just y's, we could say what is the most likely set of x's. So it all depends on the question you're trying to ask. There's a lot of different ways you can do this. It's just a matter of, these are we treat these as probability distributions. So if you have a missing value, you can kind of take an expectation and infer what the most likely missing value is. And that's sort of what, when you're recovering the hidden state, what you're doing. So does that make sense?
Yeah, okay. So it's like a tool that you can either recover the Y's or the X's or...
Yeah, you could do a lot of different stuff with this. You can actually, like I said, you can actually, just like we can generate sort of pseudo language by walking through a Markov chain. I did that, for that like Garfield thing to generate fake cartoons. You could do that with HMMs too. You can actually sample from these. You could say, give me a likely sequence of Y's, or give me a likely sequence of X's. And it can generate these based on the probability distributions that you've established behind the scenes. So, make sense? Yeah. Okay, cool.
Wait, so in case of the Garfield example what would be the Y's and what would be the X's?
So that becomes a little tougher to kind of map, because I mean, the reason we use just Markov chains instead of hidden Markov model, the reason we use Markov chains, which is basically just a string of X's, as opposed to a HMM, which is an X's and Y's, is that when you're generating sort of language, you don't really think that there's some underlying, maybe hidden process behind the scenes. So the difference between what we did for the Garfield is we basically had a chain like this. So these were the things that were the words. We didn't have these observations because there isn't like a hidden state running behind the, there wasn't a hidden state running behind the scenes sort of thing going on. So that's why we didn't really use the HMM for speech, pseudo text generation. It doesn't quite map. You probably could map it. You could, maybe there's some higher level concepts, or there's something that, I can't think of an example of sort of text generation where you'd have a hidden state, most likely. But you might have, like, it's hard to think of, in the end, people don't use HMMs to really generate, to sample from. That's fairly, I haven't heard of many use cases for that, but you could do it. The question is, can you map something where there's a set of observations that would be generated where you would sort of say, just give me a likely set of Y's, and either you knew the X's or didn't know the X's behind the scenes. I can't think of an example where you'd actually do that. But you could certainly, I mean, it's a probabilistic model. It has well-defined characteristics. So you could say, give me a very likely sample of length 10 of the observations. And you could just sample from each of the distributions, walk through it, and generate a highly likely sample of the observations. Whether you do it, I don't know. I'm not sure if there's, I can think of a really good use case where I've seen it done. Go ahead. Remember well, you don't have to remember this. There's three things we need to know. There's, for HMMs, those are the three sets of parameters. This is the probability that x1 is equal to some j. Oh, sorry. I'm going to make that a j since I wrote j there. This is the transition probability. So this is the transition from xi plus 1 equals j given xi equals, sorry, I don't know why I'm using i's. Let's do t. And this is the probability that yt is equal to j. There's actually a y here. Equal to y given that xt is equal to j. So you're basically, So this is the, if we didn't know, that's basically the start of the chain. It's the starting place that if I have no prior information, I'm not in the middle of a chain, what's the probability of that very first X? And so that's how you would, if you wanted to sample, first you'd sort of sample a state from there, then you can sample a emission, then you can sample a transition to the next state, then you can sample an emission, that sort of thing. What was there?
So just to be sure, when we have like the X goes to another X, realistically, like under the hood, there's the entire trellis of all the possible values for that X, and they all go to like the next possible value.
Okay, so this is the difference between, they're different graphs. One is the inference graph, that's what the trellis is, and that's where we've kind of unrolled all the states of X so that we can draw sort of illustrate how the information flows through to do efficient inference. Basically, that's the dynamic program. And literally, when you write these dynamic programs, typically you'll have an array that is number of states by amount of time. So you'll have a time by state array. And so that is actually the mechanism that you use. When we draw graphical models like this, yeah, each one of these can have a different value of that, or whatever our set of values are. But I generally consider them completely separate graphs. One is sort of the trellis that you do inference on. The other one is illustrating how the probability distributions depend on each other. This is more of a dependency graph. And granted, this gets unrolled, sort of the X's get unrolled to form that trellis. You base the trellis on this particular graph, but you don't. But they're very different sort of things. I mean, they have a lot of the same information on them, like what the probabilities are attached to them and things like that. But this is more to illustrate the structure, and that's more of a concrete, now I want to figure out how to do the inference sort of thing. But they do have very similar kind of conceptual things on them.
So at each of those X's is the trellis built?
Well, so really what an HMM is it's this repeating sort of pattern where this is, when we're talking about an HMM, this is really the part that is repeating over and over, right? So it's this X1 goes to X2, goes to X3 for whatever length you want. So what you do is you unroll this guy to form the trellis for the first time. So you do, if we have 3 states, this is where it gets a little complicated, because you're really saying that the trellis is really sort of drawing something like this. That you have some, sorry, the Y is down here. This is sort of this diagram drawn out like as a trellis where you have possible states inside. But remember, we talked also about how some states only transition to certain other states. So when we draw the trellis, what we do is we say this one can go to here, state 1 can go to state 1, state 1 can go to state 3, state 2 can go to state 1, and state 3 can go to state 2, or something like that. So you actually have there is a difference there. One represents, this just represents how things are chained together, how like the high-level structure is built. This one is, if we were to instantiate all possible paths through that structure, this is what it would look like. It would look like this, we start with our first time equals 1, and it has 3 states because X takes 3 states. It has certain transitions, and so we could unroll it that way. So that's how the trellis relates to the sort of the graphical model up above.
And then in the Viterbi algorithm, that's the trellis. That's ultimately the thing that gets built.
Yeah, when we're doing the actual inference, we're actually walking through that trellis. We don't really build the trellis, and I mean we use an array somehow, conceptually though. And typically you don't have, most of your state diagrams aren't that nice and clean. Typically almost every state can go to every other state, or with some very small probability. So often you'll have, like things will be going between each other with high probability for a couple things, and then with really low probability everything else. So there might be connections from x1 equal to 1 to x2 to equal to 1, 2, 3, but some of them are going to be really low and some of them are going to be really high. So it's a bit of a misnomer to say you can only do this transition. It's possible that some of the transition probabilities are 0, but if it's learned, that's probably not going to be true. So
it's kind of like a Markov matrix, and then you put the power of it.
a Markov matrix.
Because you have like the initial state, you have an ending state, the probabilities, and then it seems like every time you go to the power, it just swings to another power.
I hesitate to say yes just because I don't know quite what you mean by a Markov matrix there. Yeah, so you have a Markov, and then so if the difference is that you have observations that are being included here at each time step. So you can't just take it to another power. When you're talking about that, generally, you're talking about just a state diagram with no observations. And then each time you take a power, you're basically you're taking a random walk at that point, when you're taking a Markov, a matrix of transition probabilities, and then you square it, cube it. You're basically finding where you would end up over time if you took a random walk. But here we're not doing random walks because we have these y's that actually change which path we might be more probable. So you're not just cubing it over and over. The values are actually changing at each time step. Meaning typically in a Markov matrix like you're describing, the values of these nodes are fixed, meaning that the transition or the node probabilities are always the same independent of the time. But with an HMM, you're actually, because the y's change, the probabilities at each of the times also change. So you can't just cube it over and over.
So like every time there's the same y, is it the same the same state transition, the same probability?
Each time there's the same what?
Same y.
Yes. So okay. So each time. So again, these nodes represent the probability of. So if this is y2, this node represents probability of y2 if x2 equals 1, because this is x2 equals to 1. So these nodes represent the contribution of the y. The links represent the probability of going from some xi plus 1 equal to 1 given xi equals 1. So remember, there's two sides here. There's the contribution of this, and then there's the contribution of this. And the nodes are this contribution. The links basically become this contribution. And so you have to kind of walk through everything.
And just one last thing. So like for the probability of a given y, given the y given an x value, so they don't necessarily all have sum of 1, do they?
The probability of, say that again, probability of...
Y given the x's, like for every single x besides that.
Well, no, because you're only going to have one x. So the probability for any given x equals a value, it'll sum to 1. So the probability, let's see, the sum over all y's of the probability of, let's do y equals I of y1 equal to y given some x. This will always equal 1. So if you iterate over all the possible y's, because it's a distribution, it'll all sum up to 1. But, you know, the x's, when you have a different x, the emission probabilities are different. So when x is equal to, you know, 1, you're going to have one set of probabilities. When x is equal to 2, you'll have a different set of probabilities. But for any given x setting, when you sum over all the y's, it has to equal to 1. So that's just standard probability theory. You know, when you sum over all of the possible settings of this, it always has to equal to 1 in order to be a distribution.
I meant also like a single state, so like probability of y2 given x2 equals 1 plus probability of y2 happens to x. So that doesn't necessarily have to come up.
I don't think so. I'd have to write out the exact equation. I think if I understand what you're saying, I don't think it does. Just because you're talking about different pieces of, you're talking about different random variable probabilities of different random variables that have been selected. These are, remember, each one of these represents a random variable. So if you have a bunch of different settings of random variables, they don't all have to, you know, unless you're considering all of the possible settings, then it has to sum up to 1. But if you're talking about y1, y2, y3, that stuff doesn't sum up to 1 because those are different random variables that have, you know, some relationship. We could talk about that later if you want to nail that down a little bit closer. All right, anyways. Okay, so good review. Any other questions before we go on? Okay, cool. Okay, so we kind of have a feel for graphical models, especially HMMs, which we kind of just went over sort of the basics of again. Now, like I said, graphical models can be much more flexible. In an HMM, one thing about an HMM is we kind of have this sort of standard template that we unroll, and so it allows us to take in different sequences. A sequence of length 5, a sequence of length 10. We can use the same HMM to model that. Not all graphical models have to do that. So like this graphical model I drew right here, this one never gets unrolled. It is 3 nodes all the time. It has 3 random variables. It only has 3 random variables. No matter how we instantiate those things, there's going to be 3 random variables. We're not going to unroll that like an HMM. So that's one of the things about graphical models is they can have these repeating structures, or they can have sort of these more concrete fixed structures that don't repeat. So obviously, this kind of structure is not something you'd use for a sequence, whereas an HMM is something you use for a sequence. So that's one of the things about graphical models is they have sort of this, are they sort of infinite sized, meaning that they just sort of repeat, or are they sort of this discrete size where they have a fixed number of nodes? The other thing that we talked about here is whether they have direction or not. So some graphical models have directions. So this means that there's a dependency in a certain direction. This one means that when there is no arrow here, it actually means that x1 depends on x2 and x2 depends on x1. So that's another aspect of graphical models, whether they're directed or not. And then the third really important thing that we want that we really care about graphical models is if they're directed, are they directed in such a way that there's no loops in the graph? So if we were to unroll our graph and we don't have any loops, we don't have any time where, for instance, if we were to create a graph that unrolled somehow, even if it was like this, I could make this graphical model. That graphical model doesn't have a loop. It's considered a directed acyclical graph. It basically means that there's always a place where you can never go back. You can never get back to a certain place twice if you walk the graph. So whenever you have that sort of situation, that's a situation where we can do the trellis trick to do the inference. And this is a very important thing. If I can do this, even though there is an exponential number of different states that this graph can take, I can find the most likely path, or the most likely, it's not even a path, the most likely settings of that particular, those random variables in an efficient way if there isn't a loop. So here there isn't a loop, and that means I could create a dynamic program much like the trellis to figure that out. Same thing, we can expand that out. Let's do this. There's no reason it has to be 3. That's just how many I usually draw. This, sorry, a lot of edges there. That mangled graph, that's still, there's no loop in there. So we can still use a dynamic program to figure this particular thing out. Now, there's going to be meaning for each one of these nodes. So this one is going to be the probability of this node, let's call this x, given, let's call this, I don't know, y, just to have something. Right there. It's the probability of, let's call it x2 given x1. So this is x2, this is x1. So that's what that node is going to have. This node would have some, so let's call this y2. This would be the probability of y2 given x2. This one would actually, so let's call these guys z's. This would actually be the probability of z2 given y2 and x2. So you can make these fairly complicated. But the important thing is that this guy is still efficiently, we can do efficient inference on this because there is no loop. Because we can always start sort of at the end. In this case, you'd basically start way over here, and you sort of work backwards along the dependency chain to figure out the most probable things at each step. And the trellis, if you drew this out, would be really ugly because each one of these nodes will have some n number of states. Each one of these nodes would have some m number of states. These guys would have some p number of states. So you'd get this giant, multi-dimensional array to figure out the trellis and to calculate the dynamic program. But you could do it, and it's still polynomial time. So today we're going to talk about when you can't do that. And that's really what we want to, the most important thing that I wanted to hit today is what do you do when you cannot figure out, when you have a situation that is not tractable in this way. Does that make sense, what I'm saying, how this is a tractable thing because we can work from sort of an endpoint backwards as opposed to something that has dependencies where we can't do that? Let me give you a really quick example of something where we can't do that. So here is a non-directed. We're going to have two states, x and y. And what this means is that p of x depends on y, and p of y depends on x. Notice how there's a cycle there. X is depending on y is depending on x. There's no place to start. We can't just say, I'm going to calculate the most likely setting of y ignoring x because it'll be incorrect. And you can't say, I'm going to start with x and calculate that ignoring y because that'll be incorrect. There's no way to work, sort of from the end to the beginning to find the most probable thing. And this is the sort of situation that we're going to talk about today. How to do inference in that sort of situation. It's difficult. There's generally two methods that we talk about when we talk about probabilistic models and doing inference. One is called message passing. Message passing is just a matter of you're sort of going to, both of these methods are going to work in very similar ways. One of them is more of a heuristic, and one of them has a very solid mathematical sort of underpinning. in message passing, that's the heuristic one. Basically, you just say, I'm going to update my belief for the setting of each one of the variables incrementally. So I'm going to start maybe, I'll start at x and I'll say, you'll start with some arbitrary setting of all the values. And then you'll say for x, we're going to assume that the y is already set. I'm going to calculate my value of x, the probabilities of x, and then I'm going to tell all my neighbors about what I think my new probability setting is given my current information. And so this node basically would say, okay, given everything I know, I'm going to calculate my new probability of new distribution, and then I'm going to tell all my neighbors. And then all the neighbors get that information, and they say, oh, one of my neighbors updated. I'm going to update my belief of what my distribution over my values is, and I'm going to tell all my neighbors. And you could do that, and hopefully, there's no guarantee here, hopefully you will get to a point where there's sort of a fixed point where things stop changing. If you have a really complex network, that's not guaranteed. Things can keep moving around, and message passing can kind of stumble there. So you have to have some sort of way to make sure that you're actually converging and you're not just sort of moving around probabilities. This one goes up, the probability of this value in x goes up, and then it gets a message and it goes back down, and then it goes back up, and then it goes back down. There's nothing to guarantee that message passing is going to converge. So that's the first sort of ad hoc way. It's actually a really common way to do things. I'm not going to talk about the details of it. It's more of just the idea that you sort of treat each thing independently, and then just sort of try to update things incrementally by and forwarding out your results to all of your neighbors. What we are going to talk about is something called variational inference, and we're going to talk about variational inference because it's very useful in a couple situations, and it will come up. You don't use it very often, especially now that graphical models are kind of on the outs as a popular technique. But there are some situations where we're going to encounter both here and later on where variational inference is the way to go to solve a very intractable problem. So that's why I actually decided to do this, even though I much rather would have moved on to neural networks. This is worth knowing, worth have seen, even if you're not going to use it very often. So let's talk about an example. So we know loops are hard. We know that's the big problem. So let's talk about an example of what you might graphical model you might use here. The graphical model we're going to look at is, I reordered all of this stuff from the way that it was done last semester. So if I get a little lost, I'm trying to make it so that it's a little more of a coherent story than I thought it was taught last semester. If I get a little lost, it's because I'm trying to redo this on the fly in my head while talking. Hopefully that won't happen. But the situation, or the example we're going to look at is for image denoising. And so with an image, basically we're going to talk about hidden states and visible states once again. So when I talk about an image, we're going to have a set of pixels. And for now, we're just going to consider black and white images. Everything we do here is extensible, again, to non-black and white, to more dimensions, and to even real values. We're just not going to talk about them because the math gets really complicated really quickly. So to illustrate the math, it's best just to talk about values. So specifically, we're going to talk about the values of -1 and 1, where -1 basically means it's a black pixel and 1 means it's a white pixel. And so what we have is we have an image. And we're going to say that we had an image and we sent it over some system, and a bunch of noise got added to it. So we have the image that is sort of the real image, and again, we're going to call this the hidden variable, or the hidden image, that we don't know it, it's what we want to recover. And then we're going to have the observed thing. So we're going to have a set of nodes. In this case, they're going to be labeled H. And this is the hidden sort of real image. And then, unfortunately, we're going to have some, what are the variables X. And X is the observed image. That's kind of important to notice. We've totally changed our what an X and Y and H are now. Now, before, when we were talking about HMMs, Y was observed and H was hidden. When we talk about this, X is observed and H is hidden, is the hidden variable. And if we go all the way back to classification, typically X was the observed thing and Y was the label, or often what we'd consider sort of the hidden value. So we've come full circle on renaming all of our variable names. I'm not quite sure why we do that. I think it's more of a historical fact that the papers were, that most of these things were based on. This was the nomenclature they used. So in any case, H is the hidden image, but it's what we want to recover, and X is the observed image. And the way we're going to set this up is we're going to take advantage of something we know about images. Images generally, if you have a pixel in an image, you expect its neighbor to have the same value. So basically what we're going to do is we're going to build a graphical model. This is going to be a 3 by 3 pixel graphical model. It's a very small image. And we're going to connect all these guys up. And these are our H's. That's the real image we want to recover. And then we're going to have another set of variables, which are the X's. Connected to each pixel is the observation that went along with it. So does that make sense? So we have really two layers here. We have one layer, which is the observed image, which we assume has some noise to it. And we have the hidden layer, which is the real image, the image we want to recover, which we don't know. And that's what we're going to want to do the inference to recover. Now the links, remember, these are sort of the probabilities that, you know, this particular link says, well, more to the point, let's look at this guy way in here. This is going to be the probability of, let's number these guys. 1, 2, 3, 4, 5, 6, 7, 8, 9. And just because this is the nomenclature they use in the book, the X's actually have an index value that is, it's just another index. The index values go from, in this case, this is hard to explain, but you have H, this is variable H9, but then we're going to number this one X10, 11, 12, and so on. So we'll go all the way up to 18. And that's just because all the variables, they just wanted to have one index that went across all the variables. So you're going to have H1 to 9 and then X10 to 18. It's just an oddball thing about the way the book is written. So I'll present it here like that just because that's the way it was done. But this guy, this H5, is going to have some probability which is going to be based on H, on all of his neighbors. So H, let's see, is 2, 4, 6, and 8. 2, 4, 6, and 8. And let's see, 11, 12, 13, 14, and x14. So what this is saying is that we have some dependency on our neighbors. We want pixels in the recovered image. We want pixels to have some sort of correlation to the pixel next to them. Black pixels are next to black pixels. White pixels are next to white pixels. But we also want to have a correlation to the noisy image. So we want this guy to depend not only on the pixel, the X pixel that we observed, but all of the other settings that we want to, all the settings of the other pixels in the image. Does that make sense?
So then, ideally, you can do this model with just like the however much the neighbors matter, like hard coded. But then right here, you're saying that like each pixel could have a different amount that it cares about its individual neighbor more or less.
Yes. So so we're using this for image recovery. The form we're going to use is called a Boltzmann machine, and that actually allows us to vary what basically these link strengths are. And I'm going to write that out in just a second. So basically, when we talk about so U, we're going to say U is the set of all states H and X. And remember, we purposely numbered things from 0 to n. We didn't use any of the indices twice, exactly so I could write this equation like this. So the log probability of U given some theta is equal to I, where I is the index of each one of these possible things. It's the sum over all of the different variables times the j, which is an element of a neighbor of I, theta ij, ui, uj, and then there is a so this is the equation we're going to use to describe our model. And this is exactly what you just asked. These thetas are basically attached to each one of these links, and they indicate the sort of the strength of the amount that these things should agree. So maybe you would say that I want each one of the pixels to agree with its neighbor with a strength of 0.2. So all of these links might be 0.2, and I want it to agree with its the observed value with a strength of, let's say, 0.8. So all of these guys would be strength of 0.8. So that's one possible and very consistent sort of thing. You'd say, it's mostly important that we agree with our observed value, but we also kind of want to make sure we're the same as our neighbors. But we know that images aren't just monochrome, one color, so we're not, if we said that we always wanted to agree with our neighbor, we're going to end up with something that's basically all black or all white. If we have something where we kind of want to agree with our neighbor, but we mostly want to agree with our observed, that's probably more of a normal thing for an image.
So then now is our goal to just find a theta that maximizes the log probability of U given theta?
Okay, so no, that's not what we're going to be doing. Theta you can kind of consider as the learned HMM model. If we equate this to the HMM, we had a set of parameters that described the transitions. That's what you could kind of consider theta. That's the model. And then when we do inference, basically what we're going to say is, let's say we observe a set of x's. What's the most likely set of h's? That's what inference is. So theta is actually the parameters of the model. And then we want to do inference to recover, given some x, we want to recover some h. Now we could do other things, just like with HMMs. We might want to find, we might want to find, say, a sample of, likely images, You don't really sample from these because it's intractable. You might say, what's the probability of, given a noisy X image and a set H image, what's the probability of that? What is it likely that that the X generated the H, or rather the H generated the X? You might do that too, but most of the time we're going to say, how can we recover H given our X? So how can we recover the real image given the observed image? Now these don't have to be images. This is a general equation. I could make these, specifically if these thetas become negative, I can make those thetas negative, and that would mean that it wants things that are next to each other to disagree. And if you disagree, that means that a pixel here being white would force the pixel next to it to be black. And so that's not a very normal model for an image. It's not something you'd probably use, but there might be systems where, remember this is a graphical model, it's a general, it doesn't have to apply to images, it could apply to something else. There might be other things where it makes sense for things to be sort of have this anti-correlation as they cross these links. If you have this value of 1, you want the next value to be -1, you want the next value to be 1, that sort of thing. Now, of course, you get into trouble if you have a loop of where you're trying to force things to be the opposite always, and you have a situation where it's in a grid where you can't really, if this one being positive forces this one to be negative, there might be some self-inconsistency where you'll never be able to really converge this thing. The Z, I didn't mention that. This guy, remember these guys, this is a probability. So if we sum over all possible settings of U, it has to sum to 1. And so, and because we're talking about a log here, we need a normalizing constant. And so basically what we did is we took, usually you do something like, you'd have the probability over the normalizing constant, which is the sum of all the different settings, and to make sure it's a probability. When you take the log, there's a division in there, so the log gets changed. When you take the log, it becomes a minus. It's just something to say that we want this to be a probability, so we have to have a normalizing constant out there. It's a constant for any given theta. So if we have a known theta, there's going to be some constant z, which is the same independent of the u's. Usually, we almost always have this normalizing constant out here. It almost always gets just lost because we're usually doing like a derivative or something, and because it's a constant, it ends up going away, or we set things up so it cancels out or something like that. UI and UJ are the actual settings of the H's and the X's. So basically, if you read this, so if UI and UJ are going to take a value of either 1 or -1 each. And so basically what this is saying is that if they have the same sign, UI is equal to 1, UJ is equal to 1, then you get you increase the probability by some theta, whatever the theta is. If they have a different sign, you decrease by theta, because then you'd have 1, -1, so it'd be multiply, it becomes -1 times that. So basically when they agree, you get a theta worth of sort of credit to the probability. When they disagree, you get negative theta worth of sort of credit. Okay, so this is the general setting. This is sort of if I knew all U's, if I knew the setting of all possible U's, meaning if I wanted to get the probability of a setting of U's, meaning all of the X's and all of the Y's, then I need to take this times we got to take it across all the possible things. So U includes both the H's and the X's. So what we often are going to write this as is slightly different. We'll split out the h's and x's to write it like this. Make sure we get this right. And then this will be hi, hj. We'll often rewrite it like that. And basically what this is just saying is I've just relabeled relabeled some of the variables and separated things out. So whereas this one I was saying, let me go through all of the values. Let me take all of the neighbors. So let me go through all the indices, and then for each indice, let me consider all of the neighbors, and then I'll take the theta for the value plus it times, or the value and its neighbor. Not saying this well. So for any given I and all of his neighbors, I take theta ij of ui times uj. Now, if we separate this out into x's and h's, we can just rewrite it in a little bit different form that makes it a little more clear. So in this first half, we're just considering the connections between hidden nodes. And in the second half, we're just considering the connections between the hidden node and the corresponding x. So we go through all of the indices. We take all the neighbors, considering only the hidden nodes. And then so they're going to be a hidden node I and hidden node j. And then we're going to consider the x's also. So for all of the nodes, all of the j's, their neighbors that are neighbors of I, considering only the x values, we're going to take the same thing, hi times xj. So it's the same math. It's just I've relabeled sort of things a little bit differently. This notation I find is this is what they use in the book. I found it to be very very difficult to read. Again, it was very different from the HMMs where we just said H's had one set of indices, X's had another set of indices, and we just sort of use them in a more natural way. This one is the one where we're sort of numbering everything from 1 to 18, even though the X's and H's are kind of sort of distinct sets. But does this make sense? Okay, so anyways, variational inference. I don't think we're going to get done with it today. I think this is taking longer than I'd hoped. Anyways, so this is actually the probability that we want to, the probability of a given set of h's and a given set of x. What we really want to learn, or what we really want to compute, is the probability of x, the probability of h given x. That's what we're really interested in. And more to the point, we're interested in the argmax of this. So what we really want to look at is not just the joint probability of h and x. We want to, given a set of observations, we want to find the most likely set of hidden variables. This is very, very much how we did what we were trying to do with inference for an HMM. We're trying to recover the hidden variables. So let's start looking at some of this stuff. Just trying to piece together my notes here. So if we look at this this particular thing, this is going to be equal to again, it's going to be equal to basically well, it's going to be equal to basically this same thing right here. But we're going to have to iterate over all the different h's. And so normally what we do when we had this sort of situation is we would, when we want to find sort of the maximum, we don't actually iterate over everything. We do something like we take the derivative, set it equal to 0, and we find the maximum or the minimum that way. Now that's not going to work in this case, and this is where we're going to get into trouble. This is why things are difficult. We can't do that mostly because h is discrete valued. We can't use our standard trick of taking the derivative and setting it equal to 0 and then sort of walking down the gradient. We can't do that because the h's, the individual h's, well, and the individual x's for that matter, are -1 and 1. And so you can't take the derivative of something that has the -1 and 1 in there. There's no way to take that derivative for those discrete values. So we actually end up in trouble because we can't do that. So basically it becomes intractable, and we can't just enumerate. One thing we could do is we could try all possible h combinations and just find the one that was the most likely that formula came out to be the highest. We obviously can't do that because this grows exponentially. If you think about for each h, for each pixel that we're trying to recover, it has 2 values, and so that means that the number of settings that we'd have to try to recover, or the number of things we'd have to try to evaluate would be basically 2 to the 9th for our little tiny, so it would be 2 to the number of pixels, basically. For our little tiny one, 2 to the 9th, maybe we can calculate that. That's not huge. It's not small, but it's not huge. But if you're only talking about a 3 by 3 image, so if you have a real image, even something small like the MNIST that we looked at, where it's just 28 by 28, I think that's 784 if I remember my math. That is 2 to the 784th is pretty big, pretty intractable to do. So we need to have a system where we can find this argmax of h, which is basically evaluating all these formulas in an efficient way. We can't use dynamic programming. We can't do our trick of taking the derivative and setting it equal to 0. So this is where variational inference comes in. We'll probably need those. And we're not going to get done in 10 minutes, but variational inference. Variational inference is an odd concept. It is used only for inference. We're not actually going to be learning the parameters of the model, so we're not going to be learning things like what are the thetas. Instead, we're going to be saying, given some x, some observed value, I want to find the best setting of h. So I want to do inference. I want to actually find the values. And the way we're going to do this is kind of odd. So if we have some p, I want a letter that we haven't used before. We'll just use h. It's fine. If p of h is hard to evaluate, we can't evaluate that. One thing we can do is we can find some q of h. That represents p. And then we'll use the Q to actually get the values, to do our inference. And then we're going to use Q to get our H's, the most likely H's. So basically what we're going to do is sort of a little switch here. Is we have P, it's really complicated, it's super, this very interconnected sort of distribution of a bunch of different random variables. We can't evaluate it. So the game we're going to play is we're going to find Q instead, and that Q is going to be something that we can find, and then we're going to use that Q to determine H. Now, if we just did that sort of arbitrarily, there's nothing that drives the resulting Q, the H's that came from Q, to be the best ones that came from P. So let me draw out an example. So let's say we have our image here. And I'm just going to do 2 by 2. And then I have my x's. So we have h1 to h4. And then again, this guy is equal to some probability of, h3 given the other h's and the x. And so that's that's what we need to figure out. We need to figure out the most likely set of h's that for all of these different distributions. So what we're going to do again is we're going to find a new distribution that is easier to work with, but somehow represents that. And so in this case, what we're going to do is this is our P distribution, and this is going to be our Q distribution. And you'll notice there that it's just 4 independent variables. So this is, again, this is h1 to h4. But we've cut out the x's, we've gotten rid of them, and we've cut out the interdependencies between them. So now it's really easy for us to evaluate this Q distribution, the set of Q's. Now this looks really weird. We're like, here's this thing that has all this complexity. Let's just consider this other distribution that has none of the complexity. We threw out all the interdependencies. Why is this going to generate anything that's sensible? Here's where variational inference comes in. Is the third step we're going to do is we're going to, Q is going to have a set of parameters. So remember, Q is a distribution, a set of distributions of some sort. It's going to be parameterized by something. So we're going to have the Q is going to be the probability of H given some set of parameters which we'll call pi. Now the key is that we're going to, each time we do inference, each time we get a new image, we're going to choose a new set of parameters for these Q values. And that parameters are going to be chosen such that the output of P, if we knew it, if we could calculate it, will be close to the output of the Q's. So this is a really weird thing. I know some of you are shaking your heads. This is hard to get your head around it because it's just like we're doing some magic here. But really what we're going to do is, the thing that's going to do the magic is we're going to do some minimization of sort of the distance between P and Q. So P has some settings. We don't know what it is, but it has some settings. Q has some settings that are going to depend on this pi that we choose. And what we're going to do is we're going to make sure that those two things, the outputs of the probability, the likelihood of the H's coming out of P are really close to the likelihood of the h's coming out of Q, and we're going to do that by adjusting these pi parameters that are associated with Q. And so this begs the question, we're going to make these two things close, these two distributions close. And it begs the question, how do we do that? So we use something, a metric called KL divergence. So KL divergence is a concept that is basically measures the distance between two probability distributions. So if I have two probability distributions over the same set of variables, I can ask, are these things similar? So the definition of KL divergence, which ran away here, KL divergence, which we usually write d of one probability given the other probability distribution, is equal to the log of the probability, it's Q on top, P times Q DH. So let me before you copy that down, let me rewrite that with the hidden variables in there. This is the same exact thing. I'm just going to put the labels so you know which variables we're talking about. This is equal to the summation over the log of Q of H given X times the Q of H DH. So that's what is called the KL divergence. And basically what the KL divergence is saying is we have two distributions over the same set of variables. So we have some H and H. We have the distribution over P and Q, or the distributions are P and Q. And this is kind of the distance between those two distributions. If this is 0, that means that the H's, the likely H's will be the same. The H's that you get will be the same. They'll have the same probability distribution. So basically, when it's 0, they'll be effectively the same distributions. And it's only 0 when they're effectively the same distributions. The one interesting thing about this is not a symmetrical measure. If you switch the order, you actually get a different value. So if we want the KL divergence between Q given P or P given Q, the order of the P and Q change, and the value will actually change. Now, it's still the same. If they become, if one is 0, the other is 0, essentially, because they're the same distribution. But because we have this measure, we're going to actually be able to minimize, change the parameters of Q so that this measure goes down to some minimum, as small as we can get it. And once it's at some minimum, then Q will be a really good representation of the distribution of H for sort of as a proxy for P. And that's the game we're going to play. We're going to have to do it next time because we're out of time. But that's where we're going to be heading. Hopefully we'll only take about half the class next time for that so we can get on the neural nets. But are there any questions before we go? We are not going to have an assignment on this. This actually had an assignment last semester. It's kind of cool to see it work because it does denoise images kind of nicely. But it's one of these things that the same as a lot of last semester assignments versus this semester. Last semester we made you do a lot of little nitpicky implement this algorithm, And again, my philosophy is that's not what you do when you're doing ML. You're never going to write mean field inference, which is what this is going to be called for images. If you're a researcher in images, sure, you'll write it. If you're a normal person doing ML, you will go and you'll find an sklearn and you will use sklearn. So that's why we don't do this. On the other hand, the reason we don't actually give you an assignment to do this, like let's say we weren't going to have you actually write it, why don't we just have you do it? Because if you use mean field inference from sklearn, it's a one-liner and it spits out an answer and you're like, oh, okay, well, that was fun. So we try not to give you things where it's a one-liner and you don't have to think about it. So the next assignment's actually going to be moving into neural nets already. So we'll get you into neural nets, and we'll probably have 3 neural net instead of 1 like we did last semester. Okay, anything else before we go? Okay, I'll see you guys on Thursday. I do not know anything about it. Yeah, I don't know what they have, what they're doing for anything really. Yeah, I'm pretty. I don't, because I'm just an adjunct. I basically teach this class. I don't get to talk to the other professors about their long-term plans. So, yeah, I can't tell you much about it.
Yeah, so about the thing I was wondering about earlier. So, a single set of that is just like it's just like an easier representation of this, right?
Kinda, yes. It's a slightly different representation. This is sort of says the structure, and this you can kind of think of as if I expanded it out to indicate all of the possible paths through the graph. Like if I want to evaluate all possible paths, I write it like this, and this is basically this x can take a value of 1, 2, or 3, and so we write it all 1, 2, 3. The y is observed, so we only actually have a single y down here.
Yeah.
So it's not the same. It is definitely, you are basically expanding this to get this, but I wouldn't call them the same sort of thing. This is the graphical structure, okay. And this is the trellis that is, you run basically the dynamic program computation off of.
Okay, and in the trellis, so the values of the circles are like their weights given by the probability of this observed
Yes.
value given x. So
Yeah.
I was wondering if the sum of the weights of all of these is equal to 1 or not. I was thinking it wasn't because the...
No,
okay.
no. It is, no, that is not. Okay, so there's a typo here. Mm-hmm. This one, this is x, the subscript indicates the time, not the state. So what we're actually talking about is x
I is equal to
xi equal to 1, xi equal to 2, xi equal to 3.
Okay.
Because there's a yeah, this stuff gets hard to track what everything is, but that's important actually. And no, these will not sum to 1 because these are completely separate states. You're never in state. You know, this is it's sort of like on a probability, given this, all the possible settings of of this side have to sum to 1.
Okay.
But, you know, given a given y, if these change, they don't sum to 1. Okay. So yeah, those don't, that does not change. That does not sum to 1. Just
another thing. So if the yi for both of these were the same, then the weights would also be the same?
Yeah, if this yi was equal to 7 and this yi was equal to 7, then the weights on each one of these would equal the same. And in fact, the examples in the book, if you look through the example of doing the dynamic programming, that's exactly what they did. Is they sort of said, well, all the weights are the same. We're going to use all basically the same y's, and so all of the weights became the same. But generally, that won't be true. Y is obviously going to be changing.
So is this kind of like similar to the naive base that we did in MP1, where like these are like 0 to 9 for the states, and then the observed values are whether it's a pixel was a 1 or a 0? Is it kind of similar to that?
I mean, it's almost certainly kind of similar in some way. I don't know that I would map it like that in my head.
Is it because for each individual pixel value, the probabilities are different?
This isn't some joint probability over all of these. Yeah, all of these aren't summing together. It's because, again, we have an observed value.
Okay.
We're not talking about, I mean, if you talk about the probability, if you talk about, sort of the sum over all possible I of p y equals I given some x equals j.
Okay.
This, for all possible y's, this is going to equal to 1. When these sum up, that has to be equal to 1.
But you only see one y.
Yeah, but you only see one y at a time. For this, y equals some 7 given x equals j over the different x values.
Okay, that's also equal to 1.
No, this does not have to equal 1. It could, but basically you're saying these are totally different things.
Oh, yeah.
The probability of a 7, so given that I have, these are basically two different probability distributions. When when x is equal to 1, that's one probability distribution. And when x is equal to 2, it's some other probability distribution. And they don't have to sum to 1 at all. There's nothing that says, the givens are basically, they discriminate completely different probability distributions over this value. So yeah, that's really what you're looking at in this situation is if you summed all these guys, you're in this lower case where it's not going to sum to 1.
Okay.
It could. There's a chance it does, but it doesn't have to.
Okay.
Now, it will be greater than 0 because, each of the individual ones have to be greater than 0 in some way. Well, yeah, because they have to, there has to be some probability mass for that. But
Unless it's just something.
yeah, I think there has to be probability mass there. Okay. So I got to get going pretty soon. I just got to get out of the way. That it?
Yeah.
Okay, cool. Sounds good. What's up?
Quick one.
So in the HMMs, there was the observe and the hidden one. Right?
Yes.
So I'm still confused in a way where, so you have these all three parameters, the probability of x being
Yep.
that. Right?
Yeah,
In
it's
that
just-
state, it's just counting, right?
Yeah. You normally just. It depends on how you learn these things. We talked about last time. Like there's the counting versus the EM, depending on.
Right.
But that is the definition of the model. Like you have to use these models, you have to know those parameters. So you can get those parameters if you have sequences of y1, if you have a bunch of sequences of y and x that are tied together, you can do counting to get those parameters. If you just have a bunch of y's and you've never seen the x's, then you use that EM approach that we talked about to recover those, the pi and the 2p. Yeah, and then you use the delta and you use So there's the difference between the model and then this is basically the model parameters, and you have to recover those somehow or know them a priori.
So in the case EM,